different hearts, different dreams. Injective souls ignite the beams. No dream alone, no path ignored. Surjective wills knock every door. More hearts to thrive, or more dreams to grow. Two mighty sets now march toward battle. The wings of cardinality raise us high to the heaven of infinity, beyond the sky.
Previously, we have introduced the concept of cardinality. In the next few sections, we discuss how to compare cardinalities of different sets. Given two sets A and B, we say that the cardinality of A is less than or equal to the cardinality of B. If there exists an injection F from A to B, we say that the cardinality of A is strictly less than that of B, if there is such an injection, but no bijection between A and B. In particular, we are interested in those sets whose cardinalities are dominated by the cardinality of the natural numbers, which are called countable sets. Our first observation is that if a set A is infinite, then its cardinality is at least countable. To see this, we construct an injection explicitly from the natural numbers to A as follows. Start by picking an arbitrary element, call it x0, from the set A. Since A is infinite, there exists another element, x1 in A, that is different from x0. Continuing this way, we keep choosing x2, x3, x4, and so on. At each step, we can always find an element distinct from those already chosen. Otherwise, the set A would be finite. Now we have formed an infinite sequence of distinct elements from A, and we can define f from n to A by sending n to xn for each natural number n. Since all the elements in the sequence are distinct, this defines an injection from the natural numbers into A, thus the desired result. Now, given a countable set A, there are two cases to consider. If A is a finite set, then since there is no bijection from a finite set to an infinite set, the cardinality of A is strictly less than the cardinality of the natural numbers. If A is infinite, then by the proposition just proved, there is an injection from n to A. However, by the definition of countability, there is also an injection from A to n. In this case, by the CSB theorem, A and n have the same cardinality, and A is called countably infinite. We have already seen several examples of countable sets. Any finite set, the set of natural numbers, the set of integers, and so on. To identify more subtle countable sets, we introduce the following proposition, which essentially states that any countable union of countable sets is still countable. More precisely, the proposition is as follows. Let J be a subset of the natural numbers, which is therefore countable, and serves as an index set. For each index j in J, let Aj be a countable set. Then, the union of the sets Aj, as J ranges over all elements in J, is also countable. For example, suppose J is the set 1, 2, 3, and A1, A2, and A3 are three countable sets. Then, by applying the proposition, we conclude that the union of A1, A2, and A3 is countable. In this example, the index set J is finite, yet the countability of the union remains valid even when J is countably infinite. First, we claim that without loss of generality, we can assume the sets of interest are pairwise disjoint. That is, if the indices j and k are different, then Aj and Ak do not overlap. To justify this, take for example J to be finite index set 1, 2, 3, and suppose A1, A2, and A3 are three countable sets with possibly non-empty intersections. We can redefine them to be disjoint as follows. Set B1 equals A1, B2 consist of elements in A2 but not in A1, and B3 consist of elements in A3 but neither in A2 nor in A1. Each Bi is a subset of Ai, and hence still countable. Moreover, B1, B2, and B3 are now pairwise disjoint, and their union is equal to the union of A1, A2, and A3. This justifies our extra assumption of pairwise disjointness, and this process can be generalized verbatim to any countable index set J. Now, We construct an injection from A into the Cartesian product N2, since the sets involved in the union are assumed to be pairwise disjoint. Each element x in A belongs to a unique set Aj for some j in J. Moreover, since each Aj is countable, there exists an injection Fj from Aj to N. We now define a function h that sends each x in Aj to the ordered pair Fjx and j, which maps elements of Aj injectively into the jth column of the grid n times n. Since h maps elements from different sets Aj and Ak to different columns, that is, the jth and kth columns, respectively, it follows that h is indeed an injection from A into N2. In other words, the cardinality of A is less than or equal to the cardinality of n times n. Finally, recall that we have already shown that n times n is countable in previous sections by using either the Cantor pairing map or the CSB theorem. Thus, the proof is complete. This proposition is powerful in justifying the countability of given sets. In the next section, we will use it to study the countability of the set of rational numbers.
신라 텐세